All right, we're going to build a dotty application and try to understand some of the features in it, how they might help us improve our programming. In addition, we're going to choose the blockchain domain. There's been a whole bunch of Scala blockchain programs. You go find them on GitHub, including some very recent ones. A lot of time they use Akka for node communication, and that's all good. We're not actually going to build a full blockchain, but we'll illustrate blockchain concept and use sort of in the first pass a very imperative looking code, and then we're going to revise it again in dotty. First one will be in dotty, the revised will be in dotty. We'll use some functional programming concepts that hopefully will reduce the types of errors in our code, and we'll actually see very dramatically how immutability can remove an entire class of problems in our code, and how some of the functional programming concepts might make sense. So let's go ahead and call it dotty chain. We're going to use mill. So first thing we need to do is import some things, scala lib that mill needs, and then we're going to do a dotty trait extends. So we're doing all this from scratch basically. So hopefully it'll work out. I think that's scala module. Let's see, Scala version. The latest dotty for this is 0.26 RC1. We need to define some scala3 options, and I think I like y indent colons. Significant white space is on by default in the latest dotty. And let's see, but I need to add something that this helps with some additional colon syntax. Let's see, bouncycastle.org. Let's see, Java home, sure, let's go there. I need the latest releases. I'm going to take that one because it has OpenSSL in it, which is the one I usually use. So org bouncycastle. Let's see, BCPKIX JDK150. This is very manual, but it's good enough. And that we'll do example one. Let's see, object example one extends dotty trait. And I think we need to define what the main class is. So example one. Let's call it example 1.1. There we go. Kind of be goofy. That's all we need for the build file. So let's go ahead and start up Visual Studio Code, which is a good enough editor for our purposes. All right, we'll make it a little bit bigger here. Let's do make dir example one source. Go. All right, so we're kind of on our way to build a little blockchain. And what we're going to do is we're going to start backwards from program that we want to write, and then kind of work into the implementation. So here we'll say main def example one. Example one. I'm going to print out what we're doing. And if we're going to need a blockchain, then there's probably something called blockchain. We're going to add some blockchain blocks to it. So something that says, let's see, add block. Let's define a hypothetical block that has a index number in it for the block sequence number. It has a date, which we'll just model as a string because we're a little bit lazy. It takes a vector of transactions. So we'll say transaction with an amount of 4. And let's add one more block. So we got parentheses here, and add block, and we'll just kind of do the same thing that we did up there. And the details again are not too important. Obviously, we want to be a little bit more careful about this if we're building a real blockchain. So now we print it out. All right, so here we have our main program, which is let's create a blockchain, add some blocks, and then print it out. So now we're going to work backwards from this and see what we get. So in dotty we can say class blockchain, and because it has a creator function, we don't need to say new down here. That sounds good. So let's have a chain. And we need to add blocks to it. So it sounds like initial thinking we need to have a mutable chain. So let's put in a mutable list buffer just for fun. And now we can say list buffer the hypothetical block, and we'll say create Genesis block. There's usually something like that we need to do. So create Genesis block, and that's going to be a block 0 and some Genesis date and no transactions. How about that? Let's see, we probably need to get the latest block at some point, so we'll say chain. Let's see, chain length -1. We always have at least one element because of the Genesis block, so that's good. And we need to be able to add a block, so let's say new block, and we're going to return unit. That indicates that we're mutating a blockchain instance. Now we know that blockchains are connected via hashes. What that means is that each subsequent block has a hash for itself, but also carries the hash of the previous block. And that acts as sort of a link between blocks so that you know if the hash changes, then something was changed in the block. So what we need to do is if we have a new block, we need to tell it, this is the naive coding, previous hash equals latest block, hash. And then, let's see, new block hash. We need to really recalculate the overall block hash because we just changed the linkage structure in that block. So new block, calculate hash. We have to write that function apparently. And then chain, add one new block. That's good. We're going to want to have a better toString. So let's override toString. And we'll say blockchain. And let's see, what do we want to do? I think we're going to just need to do chain map. Keep it real simple. Make string. And that looks good enough for a blockchain. And then we need to find a block. So, you know, I think for the block, we could do a case class. They're still available in dotty. Block, this means that it creates the new function and copy function automatically for us. So, you know, they're kind of a good thing, but let's just kind of, you know, be very imperative and simple thinking for the moment. Timestamp, string. Now we're going to make the set of transactions that go into a block mutable so we can change it down in the example program and corrupt the block. So let's make that a var for the moment. And we might make it a var because we want to intentionally change it for this example, but perhaps if we're not paying careful attention, we made it a var or it's a Java class or something else like that. But the idea is that for some reason, perhaps it's mutable. That means we can corrupt it, which is what we're going to do intentionally here. So now we need to have previous hash. It needs to be a string, and it's going to be like that. And I think we need to have another hash. So anytime that you create one, it's going to calculate its hash immediately. And now we can write the hash function for it, which should return a string. So to do the hash function, we're going to use the SHA-256 digest that is available in Bouncy Castle. That's also available in the JCA API, so you can just use straight Java if you want. But I need to go find that class. Is it down here? Coders. No, let's go look all classes. Obviously, I could just use completion in my editor to find this, but you know, I like looking at the docs actually to get a sense of the library if I haven't used it before. So I know it's here somewhere, and here it is. So I'm just gonna cut and paste it because I'm lazy. Import that. All right. So to calculate a hash, we want to calculate a hash. We could use the Java hash function, which automatically takes a Java object and computes a hash, but that's not stable across invocations, and it's not stable across programming languages. So we'll use the 256 digest here to create a 256 byte hash for it. That's not critical for what we're doing or to know that, but we'll do 256 digest very simply. And we need to output a 256 length set of bytes, which represents the hash itself. So we can just get the length right from the hash there. And now we need to take all these pieces of information and put it into the hash. Some of these are strings and some of them are integers. So index string is equal to index to string. And then we have a data string is data map to string, and make string. And now we need to use the API for this. So if you're familiar with the message digest APIs in Java, what you do is you create an object, you add things to it, and then you eventually finalize it. And then you can return it. So it's basically a builder function. So we need to add in the different bytes. So we're going to get the bytes from the string. Data string plus timestamp, make sure it's all in there, plus previous hash. And then get the bytes, place it into position 0 inside of the digest builder object. And now we just need to get the proper length. So previous hash dot length, timestamp dot length, and let's see, I got data string. Nope, I don't have data string dot length. There we go. And once we have that, let's go ahead and convert the output to hex string. And for that, I think this is going to be about right. Char set ETF. We'll say until it's 8-bit character, so it means it's a byte. Now we don't have the hex function, so I need to go get that. I just happen to know where it is. You can find it almost in any library that's out there, but we'll use the bouncy castle one for fun since we're using that library. And now we just need to say import. I think we're almost done here. Let's see, what else do we need to do? Well, now that we got that kind of working, let's, or at least we think is mostly complete, let's go to a terminal, and we're going to run mill in watch mode, and it's going to watch for changes and then rerun stuff. So it's pretty standard, but it's super easy with the -w flag, and let's kind of go like that. Hopefully we don't have any errors here. And while we're doing that, let's go ahead and start doing something that allows us to mutate the block and then determine if it's been mutated. So let's we're going to do something that says print line valid. Let's see here, blockchain invalid blocks, then print line BC. Oh, we actually have to mutate it here. So let's see here. We're going to do that twice, and in between we're going to mutate it. So let's see, hopefully I got that right. All right, so let's see, blockchain, going right into the chain and change block number 1, which is actually this block right there. And what we're going to do is change the data. So let's make it transaction 10,000 or 100,000. There we go. That looks really exciting. Let's see. A little bit of a build file error here. So let's kind of see what we got. Object example instance dotty trait. Scala version. Little capitals. There we go. Hopefully that will take care of it. All right, so we have our program here. What we've done is we're now going to print out the blocks, and then we're going to change the blocks. And so now we need to write an invalid blocks function. So let's go ahead and do that. That's while it's compiling. Just to let you know, I'm using a 10-year-old laptop to record this, so it's actually a quite slow laptop, especially when it's recording something. So let's see here. Now we need another list buffer. We'll do a very imperative algorithm. Dotty allows you to change the way you write for loops. We're going to write basically imperative do loop. Perhaps not always our first choice. So let's get the previous element. Let's get the current element. And then if, for our logic, determine if a block is invalid, we'll just do 2 checks. We'll recalculate the hash. Whoops. Or we'll check the current hash, or the hash of the previous link. And then we go there. And given that we have that, we can then turn the sequence. So we're doing something very simple using some of the new dotty syntax that's here. And we have to define a transaction. That probably would be very helpful. So we'll say a case class transaction amount is an int. And just like before, we'll do a override to string. And in this case, we'll say transaction amount equal amount. All right, we'll keep it super simple here. All right, let's see here. I just have a couple errors, which would not surprising, given that I was just typing it a little bit off the top of my head. Let's see here. I got to hit save. What else do we have? Oh, looks like forgot my def. There we go. All right, so roughly speaking, that should probably compile at this point. And what we're going to see is let's see here. Coders hex. Too many arguments for constructor hex. Oh, okay. Well, that's because it's hexacode. I happen to remember that now. All right, so let's kind of go through this and see what we got. Here we got things that we probably don't like, which is mutability. And we'll see if in a minute why that might be good or bad, but in general, it's not going to be great. We made this var specifically mutable because perhaps that's our default for how we program, but we also needed to be able to change the chain, show how it could be corrupted in code. And so if we had programmed that as mutable, we actually directly showed that we can corrupt the chain right here by inserting a new transaction. Now with blockchain, we can detect that that actually caused a problem, and then we can detect where and what block specifically the corruption occurred. So that kind of helps us offset the fact that it is mutable. But in general, we don't want to, even in our code, be able to make mistakes like that. We also saw that this is actually quite messy. Since we want to have a Java independent, means that this needs to be a sort of a strategy argument, right? We need to be able to change the way that we encode the information in a block into the hash. So we'll probably make a change there. We see more immutability here. We see an imperative do loop, which is, this is actually not reusable. There's actually 2 parts to this, which is traversing, and then there's applying a predicate. So in general, we see that we're actually mixing 2 things here. That's not necessarily bad if that's all we ever do, but if we want to change the way that we detect invalid blocks, or if we want to loop over the blocks for another reason, perhaps we can separate out this function to be a little bit more interesting. Here we saw that we're actually doing a lot of mutability. And if we did not know that we were doing this inside the function, if we didn't read the source code, we wouldn't really know that this block is being changed inside of here. Obviously, the source code tells us, but if the documentation didn't tell us, we wouldn't know. And we might be surprised when programming that some of this information has changed. For example, the hash, previous hash, or the current hash of the block. So we see a lot of structural issues with this. As we printed out, we saw that we got the blockchain. We need to make sure that we've actually added all the blocks properly here. Let's see here, add one new block. Okay, so here we have the blockchain, block 0, our genesis block, block 1, and block 2. So we have all 3 blocks. We saw that when we calculated whether it was a valid blockchain on the first pass, there were no invalid blocks returned. And on the second time, after we corrupted the chain because our data was mutable, so it was quite easy to do, it turns out that we can detect that only with the blockchain and the hashing. If we weren't doing blockchain, we'd have to have other techniques to detect when something has changed, which may be significant to us. So we see here that the blockchain inherently is about immutable data, or at least it tries to be. And it offset mutability in our programming code, but we like to do better. And so the question is can dotty help us do better? And I think it can. So let's go ahead and make a change to our current dotty program and use dotty functional programming features. Very simple stuff to see how that works. So to make the change that we're looking for, let's go ahead back here, and we're going to just copy the example as is. And now we're going to bring up the example. We'll kind of shut down the old one. And down here, we're going to convert this to 2. And we need to tell our build there's now a second example that we're going after. So let's go ahead and do that. And example 1, 1. That's now example 2, 2. All right, import changes. And then down here, we're going to say example 2, and at the top, example 2. All right, so now let's kind of take a look and see what kinds of things we can do that might help improve the code a bit. So dotty has a number of features. One feature, for example, is extension methods. And let's see how we can apply extension methods to maybe clean up the use of the digest. The digest is actually a builder function. You can call update multiple times. It'll keep adding the content one after the other into its little internal buffer. But here we create a giant string and then add it. So we're actually kind of doing double work. So one thing we can do is maybe help clean that up a little bit. We'd like to call update multiple times, but maybe chain the calls together. We looked at the API, you can't chain them. You have to call md.update multiple times online. So let's just write a simple extension method. And let's do the superclass of SHA-2256 digest is going to be the general digest. And let's do an extension. We just need to do an extension like this. Def update, and we're going to add in all cases a byte array, so that's not going to change. And all we need to do is say d update b0 and b.length, and then let's return the digest so that we can chain things. So now we can actually change this to something a little more interesting. So we can do something like this now. So now we can do index string get bytes. We can do data string get bytes. We can do, let's see here, previous hash get bytes. So clearly we could also make an extension thing for just doing a string here. So def, I'll just leave it as bytes for the moment, just to, we're going to lose anything here. Index data, timestamp. And we get rid of all this stuff. So, now we've at the very least been able to convert this so that it's a little bit easier to use. So that's nice. And we need to go back here. Let's just import everything. There we go. All right, so extension functions allowed us to clean up a lot of code here fairly easily. In fact, we'll do this. We'll make another revision here shortly around that. But let's just kind of keep going through and think through the types of things that we want to correct. So one thing we noticed was that down here we were able to actually corrupt the chain directly in our code. Now the chain could get corrupted on disk, it could get corrupted by mischievous players, but we would expect our programming code to protect us from being able to make that change. So let's go look at the blockchain class, and we're going to make a change here. We're going to make this a case class, and instead of keeping that chain as an internal variable there, we're going to say blocks, and that's a vector of block, and we're going to say blockchain create genesis block. And we see that create genesis block doesn't actually depend upon the class itself, so we'll go ahead and move that down here. And we'll just do that. All right, well, it kind of helped. It's going to cause a little bit of problem here. Right, so now we have a problem, which is a lot of the data in here is not going to be mutable, and we have all these mutable functions. So that's a little bit of a problem. This function actually, keep this one the same. And let's see, did I spell genesis block correctly? I think I did. Blockchain, I got to capitalize that. Uncapitalize it. There we go. So now we need to change this class some more. So let's do the invalid blocks change. Here we had an imperative do loop, which actually had both traversing or finding as well as applying a predicate. So why don't we kind of say invalid blocks is going to really be equal to find blocks to satisfy the predicate. Let's take the previous, or take the current and the previous, and then we can apply some logic. If I'll say current dot calculate hash does not equal current dot hash, or current dot previous hash not equal previous hash. All right, now we've actually made that a function, and so this actually becomes find blocks. And here we're going to have a predicate, which is a block, return a Boolean. This is a pretty standard approach for doing these kind of things. Now we can get rid of that. We can now kind of also look at it and say maybe we can do something a little more clever that keeps it more functional. This do loop, writing this do loop, we can have these i's and these ones and things like that. Nothing wrong with that, but if all we did is we could use something called fold left, and a fold left is going to take some result or some information and propagate it as you visit each element in the list. It's like a little visitor pattern, but specialized for a list. In this case, we're going to give it some information that it's going to carry with it, which is the answer that we want, which is which blocks are bad, and we're going to give it the first block, and this will actually be the previous block on each iteration. You'll see that here in a second. So now we got that. So let's now we can say we got the state, we get the current, and we'll do this. And now with the fold left, what we're going to do is say return value is going to be in that little state piece of information in the fold. The previous one is going to be what we pass back. And now if we say predicate current previous, then what do we want? We want to return the accumulating result. So let's add that in. Otherwise, we just want to return, if it's an OK block, we just want to return whatever accumulating result we have and the current element as as the new previous element. So let's do that. And I can just get rid of all that. All right, so now we've structured that a little bit better as a fold, fairly simple operation. And now we see that invalid blocks can actually reuse this logic. So if we want to change the predicate, we could do that. This is a higher order function now because it takes another function as an argument. So it turned out that it makes it completely reusable if we want to change our logic or use this find blocks for some other purpose. All right, so that feels like it was useful to do. And what we need to return just the first element of the state. There we go. All right, so we've made a couple changes here. Let's go back and look at this mutability. We're getting a new block in, and then we change it. So let's go look at our block definition, because we don't want to keep this block being mutable. We want to kind of get rid of that. So right now we have these variables in here. First thing we can do is change that to be immutable, and that immediately will cause an error down here for us because we can no longer actually start changing blocks in the chain with impunity. So that code will actually not compile. In fact, what we've just seen is that by going immutable for some of these data structures, we get rid of an entire class of problems that somebody's overriding and hurting our blockchain inside of code. Now, the blockchain can still be corrupted on disk or in transit or by a mischievous player, but at the very least, it's not being caused by our code. So that's a good thing. All right, let's see here. We want to change block to be immutable because we want to get rid of this immutability or this immutability. Right now, we have still this being mutable and this being mutable. So what can we do? Well, the standard trick for breaking things apart so that you get the immutable part and the mutable part separated is we'll just create another class, and we'll just kind of copy the fields that don't change in all this. So that'll be these. And maybe we'll call block to be an info object, and then the previous hash. And then we'll do that. So now if we need to change the previous hash, we can do that because that's something we can copy this block object, change the previous hash value, and we have a new one. We still have this hash down here, which is a problem. But it actually, if we're going to make block immutable, then we can just change that to a val, and anytime we calculate a new block by copying the existing and maybe changing the hash, this will automatically recalculate the hash for us. So that's nice in the sense that now nothing is actually mutable here. So we're going to go ahead and change this, and because we changed that to block info, we're going to say add a block info. And down here where we say add block, that's now a block info. Yay, right? And let's see, what else can we do here? Now we have to go for the add block. So now, if we have a block info, we can say that's no longer mutable there. I can change all that code. And now we're just going to say the block to add is block new block, and previous hash is equal to latest block hash. And now we just can say copy ourselves, but blocks is going to be the addition of the new block. All right, so now we have an immutable data structure, and now that the blockchain is immutable, we see that we need to say, I'll say version 1. And then version 2. Oops. There we go. And that needs to be version 2. All right, so we've made a lot of things immutable now. We used some folding instead of an imperative loop. We did a higher order function, which was nice. And a little typo there. And we started kind of cleaning up the code. Now there's some more things that we can do. For example, here we call get bytes on this object, which is a string. But the original value of that was an int. So one thing we could do is use the new type class facilities in dotty. And we'll say 2 bytes t. Because we want to control how bytes are generated from an object. So let's just generate a new 2 bytes. Instead of get bytes, we'll call 2 bytes. And that needs to return an array of byte, just like anything else. But now we can say, given 2 bytes of a string, that the extension is actually just get bytes. And of course, I got to type get bytes correctly. Given 2 bytes of an int, that extension is going to look like this. And let's see, we need a Java NIO byte old trick here. Need the length, put int I array. So that's just knowing some of that Java API comes in handy. Now we have these 2 type classes for a string and an int. So we can actually come down and we can go and say, instead of get bytes, we can now control it based on the scope of our givens, 2 bytes. We could also pass in a little class or some higher order functions that convert various types into bytes, but we did this with a type class instead. All right, so that's looking a little better. We still have these 2 strings in there, but for the moment, let's kind of not worry about that. Let's just make sure that we can compile. Oh, we don't need this anymore. Well, we can do this instead of index, and data string we'll keep for the moment, but this needs to be info.data. And let's see, what else do we have here? This needs to be info.timestamp and info.index. There we go, because we changed the definition of the block. All right, so let's see how we're doing. A couple cleanups, so I forgot to hit the run function. All right, so now we've made a bunch of changes. We're a little bit more functional than we were. We're still not as functional as we could be. We'll make probably one more change to illustrate type classes again, which are useful in limited circumstances. You don't want to overuse them, in my opinion. But let's see how we're doing here. In fact, let's go up and kind of get ready for that change too. This will be our last change. So what we want to do is create a show trait, kind of like in cats or scala3. We could call it something else, but we'll just use a show. And here, given an instance of t, a show should return a string. So given a show of a transaction, what do we want? We want extension t transaction def show string is equal to, and I think we had a definition down here, so we're just going to steal that, and we're going to clean up that class. That looks a lot better. Now we have to do something for block info, so show block info, and it's the same thing, rinse and repeat. Let's see here. Now for the block info, we can kind of take, we can do something like, let's see, what do we want to do? Index equals b dot index. Timestamp equals b dot timestamp. Oops. A little spelling. Almost done here. And then data equals b dot data, and we'll do show make string, comma. All right, that's looking better. Now let's get the right number of quotes in here. There we go. Let's see, index, timestamp, and data. That's all that's in a block info. And then for the trick now, to recursively use block info's show inside of a block, we're going to say block show using show for block info as a show.block. All right, that kind of makes sense. So we're going to compose, we need sort of the recursive definition of show. So extension b dot block def show string. And now we can keep it pretty simple, which is block. Let's see, b dot info dot show, and then previous hash equals b dot previous hash. All right, and we need a couple quotes on the end of there. And let's do one more, which is a given for blockchain show. And here we're going to be using a show block info or block. We have to type one of those in, I think. Let's see here. Oh, we already got it. So now let's define it a little bit better. There we go. Call it chain. And for this one, we just need to say that it's composed of blocks. So we'll say blocks.map show, make string, and a couple more little quotes in there. There we go. Hopefully I got my count right. Hope I need a little bracket. There we go. All right, so now we've converted that, so we don't need any more two strings, and instead of print vt, we'll say print show. And now let's take a look at our errors and get those corrected. So let's see, object blockchain. Looks like we have a bunch of errors. Not a surprise. Let's see here. Hold left. I think one more. And then let's see here. Oh, add block. Value add block is not a member of unit. Okay, well that's clearly critical bit there. So on add block, turning a copy of myself. So that should have been okay. Let's see what other errors we have. Oh, not found B. So I'm going to do a little bit of debugging here. Let's see, 22. Keep it real simple. And let's see. Oh, that's almost about it. So down here, create Genesis block. It's like we're getting to the last of the errors here. This is info, but then we need block, and the hash we're going to make simply 0, since it's a Genesis block. All right, we should take care of a bunch of the errors. Let's see where we're at. Yeah, we just have one more to go because I spelled block wrong. All right, so that's line 22, and that. And let's see, add block, block BC. Oh, turn unit, I don't want that. Yeah, and there we go. All right, so really easy to do. We could also just click on these things and it'll jump to it in our editor, which would be a lot faster. All right, so now we've converted this to make it more functional. We didn't do everything that we could do or redesign it to save the world, but we did eliminate an entire class of errors. For example, we can no longer corrupt the chain in code. still be corrupted in other ways, but we can't corrupt it from a code perspective. We also saw that we cleaned up the imperative loop, and we actually made this more reusable. So find blocks, it now takes a higher order function, or it's a higher order function because it takes a predicate. That's pretty standard these days for functional programming. And we also saw that blockchain became immutable, and so every time we make a change to the blocks, we have to create a new blockchain object. Same thing for block. And to separate out block, which had a lot of mutability in it, until we broke it into the immutable part, and then left the mutability for the part that needs to change. And every time we change it, we actually would just create a copy of it if we need to. We used the extension methods in dotty to clean up some of the code, created 2 type classes fairly easily, and I think improved the readability. So eliminated errors, possible errors, cleaned up the code so it's easier to read, and kind of shrunk the code down so fewer lines of core algorithm code. So from my perspective, that worked out pretty good.